about data visualization for machine learning practitioners. And we are really happy today to have between us Julia Silge. She's a data scientist and software engineer at RStudio, where she works on open source modeling tools. She studied physics and astronomy, finishing her PhD in 2005. She worked in academia, teaching, and doing research. And so before moving into data science and discovering R, as she said, so she's both an international speaker and a real-world practitioner focusing on data analysis. And we are honored really today to have Julia between us. So let me just briefly introduce to you RStudio Tunis. In fact, RStudio Tunis is a local chapter of RStudio Global, an organization that promotes gender diversity in the R community worldwide. We aim meet up in person or virtually to learn about the programming language R, algorithms, and we are a group of Tunisian ladies passionate about R programming. We are from different backgrounds, data scientists, bioinformaticians, biostatisticians, and so our priority is to provide a safe community space for anyone identified as a minority gender who is interested in working with us. So we exchange materials, discuss any issues we have in working with us, and we receive always and are always sharing updates about it. So we are really part of a great community. So now I think it's time to start with you, Julia. So dear participants, before starting, please feel free to ask your questions in the chat below as we go along, and we will be glad to treat them at the end of the talk. So the floor is yours, Julia. Thank you.
Thank you, and thank you so much for having me. I am really happy to be here with you all. So I am here to talk to you about data visualization for machine learning. Data visualization is an important part of the machine learning process in a couple of different ways. We often talk about data visualization as one of these key communication tools that we have when we're talking outward, when we're communicating and going outward. But what I want to talk about today is how we use data visualization as a tool to make better modeling choices, as a tool used by system designers and operators themselves. You know, if we're people who use data, and the tools of like making plots, making charts, the tools of data visualization are one of the core things that we do. One of the core tools that we have for anybody who use data, any kind of data practitioner, not just people who build models or who do machine learning. And a lot of what we're going to talk about today is true because data visualization is so effective at surfacing information to human beings through our visual channels. And so when it comes to data, these visual ways of perceiving information, they form how we think about the work that we're doing, how we understand the problems that we're solving and these models that we're building, and how we decide. And I especially want to focus on data visualization as a support or an aid for decision making, because building models and machine learning systems is this very complicated, involved task. And I want to frame the plots and the graphs that we make the way that Tamara Munzner does here. So we use our computers and our code-based systems to represent the data sets that we have for a specific purpose when we're building models. It's to help us ourselves carry out the task more effectively. The task of building models and machine learnings. So this purpose building, of using data visualization during modeling machine learning is so that we are more effective at it. So when it comes to models of machine learning, more effective can have a couple of different meanings. It can mean more accurate. It can mean more practically appropriate. It can even mean more fair. And we're going to talk about a couple of different these and dig down a little bit. So I work on an open source framework in R for modeling and machine learning called Tidy Models. And a lot of the examples that I'm going to be showing today use Tidy Models code. So the motivation and some of the goals of Tidy Models, the Tidy Models project, are to provide a consistent and flexible framework for real-world modeling practitioners, beginning from like people who are just starting out in their modeling journeys to people who are very experienced people. Another goal is to harmonize the heterogeneous interfaces that we have within R, and also to encourage good statistical practice through the design of the APIs. And I'm glad to get to show some of what I work on and build. But a lot of what I'm going to talk about today is not specific to Tidy Models. So if you use some other framework for your modeling, it applies. In fact, a lot of what I'm going to talk about today is not even really that specific to R. It's a bit bigger picture. We're going to focus on these data visualization practices for real world folks engaged in building models. And we're going to start by asking this question: when do practitioners build data visualizations? So asking this question requires us to think about the process of model building itself, and to like build a picture in our minds of what the process of model building is like. So I'd like to put this out there as a schematic of what might happen in a typical process of a modeling practitioner getting from the point of first seeing some data for the very first time to having a working model. This process starts out with exploratory data analysis, EDA, and this is this systematic, iterative process of exploring data to investigate it. After this comes feature engineering. This is the task of transforming our original variables to a more useful feature for whatever model it is that we want to create. After this comes model fitting and tuning. I represented this here with a lot of little skinny bars to emphasize that when we use good best practices here, typically we don't just fit one time to all the data that we have, but instead we use resampled data sets. And so we fit and tune and fit and tune and fit and tune. And typically we don't know ahead of time which one model is going to work, but instead we have multiple models, and we must empirically test out and find which of these models is going to work better. At this point, we are then in the model evaluation stage, where we will measure how well the models perform using some metric that is appropriate to that specific kind of model and problem. Notice here, though, that we're not done. We're not done at this point. This process is iterative. We go back. We take what we have learned from the first round of what we were doing, and we go back and we do more exploratory data analysis, because some questions have been raised by the process of doing through the model, and then we spend more time creating more effective features, and then we go back, say, to the two models that performed the best, and then finally we come back to model evaluation again. Also notice that this process is ending with some goal or output. That could be communicating the results to stakeholders, or deploying the model to some kind of production system. I represented this here with a pretty thin bar, but really picture that transitioning to a whole other set of tasks. So in this talk, we're gonna keep our scope on everything before that, on this iterative process of building the model itself. So machine learning practitioners can, of course, build plots at any point during this process, but I want to make the argument that there are two phases of the modeling process where practitioners use data visualization the most. The first of these is exploratory data analysis, EDA. I said before that EDA is this iterative phase of investigation, question generation, and refinement, and exploring. So this is a phase that some people might consider before or outside of modeling and machine learning itself, but we're going to see how the investigations and understanding gained during EDA have a huge impact on the models that we create. The second phase is, there we go. Okay, the second phase is model evaluation. This is the part of the modeling process where a practitioner has trained multiple models and is assessing, is measuring, is comparing how well they have performed. So if you were able to come and like look over the shoulder of someone building a model, I believe these two phases are the phases where you would see someone creating the most plots. And using visualization in a lavish way at these two phases of the process is a sign of a healthy process. The reason why is that these two parts of the process are the points of most important human decisions. These are decisions where validation of them can be difficult. You might hear, you know, the phrase like it's like art, not science involved sometimes, and that's because it's full of trade-offs. Practitioners have to weigh different priorities and make trade-offs at these two, mainly at these 2 points during the modeling process. And visualization is used as an aid or support to carry out this task more effectively. So let's learn more and let's dig deeper into these two phases, and let's start with EDA. Let's ask this question: why are these plots built? Why are these exploratory data analysis plots built? At a very high level, these plots are built to understand the data. When a practitioner starts out, this is one of the first substantive tasks being faced. And the reason that we as practitioners need to have this understanding of the data before we even start the modeling process is because there's about to be a whole bunch of decisions to be made. The data visualizations made during this part of the process let practitioners ask and then refine specific questions related to the modeling goals, like what kind of model is even appropriate. This then feeds into the feature engineering phase that we talked about before, and what kind of pre-processing is needed. And all these kinds of questions are ones that machine learning practitioners ask, refine, and answer by making plots during the EDA process. So let's look at what a couple of these actually look like. So some of these plots take the form of very familiar statistical graphics, like this scatter plot. This plot uses a data set called the Palmer penguins. It's penguins that are observed in Antarctica near Palmer Station, and it maps each observation to a point on the plot with aesthetics of the plot, like the positions, X and Y, the size, and the color, representing things that have been measured about these penguins. So exploratory graphics like these are important for modeling practitioners because for starters, they help us understand the type and the amount of data we have available. And then going further, they visually highlight relationships in the data that we can use in feature engineering and in models. So if we wanted to build a classification model to predict the species of the penguins or the sex of the penguins based on the other characteristics that we have measured about them, then the relationships that we discover or uncover or highlight in a graph like this inform the steps that we take moving forward. Plots for EDA don't always look like those super classic statistical graphics. In some way, this is also just a scatter plot, but the mapping between what is between like the X and Y is different. It is in fact a map. This is a map. So what is showing here is a data set of trees in the city of San Francisco. And these empty areas are famous parks. That biggest empty area is Golden Gate Park, like the most famous park in San Francisco. And the other empty areas are smaller parks. The color maps to who is in charge of maintaining each tree. And so right away, we've learned something about this data set. The trees in the parks are not in the data set. And if our goal is to build a model to predict who maintains each tree, a plot like this has so much information for the person creating the model in terms of what model we might want to try. Do we expect the spatial predictors to be important, and what we're learning about the data set just from using this visualization as a tool in our process. So machine learning practitioners during EDA make many different kinds of plots. And so it's important that the tools we use for visualization during this phase facilitate fluent iteration through lots and lots of different kinds of graphs. So I have personal experience with decades of various kinds of scientific plotting tools. And in my experience, I think that learning about internalizing and the concept of the grammar of graphics is a huge step in this kind of efficient iteration. And using a system that implements the grammar of graphics to get us a big step forward in being able to quickly and efficiently ask, refine, and answer exploratory questions to get ready to train models. So ggplot2 is arguably the best known system that implements the grammar of graphics. And almost all the plots I'm showing here in this talk are plots I've made myself in the course of training models using ggplot2. And one of the first questions that we answer using it is this question: what kind of model should we try to fit? So let's say that we might want to just start with a really straightforward model, linear regression using ordinary least squares. In tidy models, one of our goals is to harmonize the heterogeneous interfaces that we often find in R's modeling ecosystem. So what we do is we separate the kind of model we want to train, like the kind of algorithm we want to train, which here is linear regression, with the computational engine we want to use, which here is LM, meaning just like basic ordinary least squares trained by R. So let's say that during the process of EDA, during the process of exploratory data analysis, I learn that there are many, many predictors. There are so many predictors that I am concerned about overfitting. I'm concerned about overfitting, and I decide, oh, I really should try out a model that will help me not overfit to my data. And so I want to try out a regularized model as well. And so I can use the fact that I knew about this large number of predictors to try a regularized model. So in tidy models, I can fluently switch back and forth between LM, basic ordinary least squares, and using GlimNet, using regularized linear regression by switching out the engine. And nothing else has to change. I don't have to change anything else about how I prepare my data, how I pipe in my data. This is one of the goals of tidy models. One of the design purposes of tidy models is that nothing else has to change about how I'm specifying my model. Let's say in a different situation, I learn during EDA that there are many, I can observe that there are many interactions between like complex interactions between variables. And I see, you know what, a linear model is not going to work very well. Tree-based models, like random forest models, are good at learning interactions between variables. And so I say, oh, I want to try to use a random forest model. I would specify it in tidy models like this, with random forest is the kind of algorithm I want to use. I can set the engine, and here I would use the Ranger package to do that. But if I wanted to use a different random forest implementation like Spark or than just latitude and longitude, but you can see just initial map that there were, and if you remember, that outcome was not a continuous variable, but a categorical variable. It was a label. So we need to build, this is something that we just fluently change using this framing of how to specify a model. So this might just be the most basic thing, and so, even something just as simple as this. What kind of model is appropriate is something that model practitioners learn from EDA, typically through visualization. The next thing that we typically move on to is what data pre-processing steps are appropriate. What feature engineering do we want to do? In tidy models, we capture data pre-processing and feature engineering in the concept of a pre-processing recipe that has steps. So you define your the variables you want to use, and that's like the ingredients of a recipe. Then you define the steps that you want to implement for your pre-processing or your feature engineering, and then you prepare them using training data, and then you can apply them to any new data set like testing data or new data. So the specific feature engineering steps are typically chosen because of what we learned during EDA. Now let's look at an example. So this is a data set of houses in a city in the United States, in Iowa. So we have a lot of information about the houses, like how big they are, where they're located in the city, and how much they sold for, the price of the city. So this plot shows the sale price on the y-axis and the latitude on the x-axis. So there's a big hole there, and that's where the university in this city is. It's called Iowa State University. So it's a hole, and then there's kind of some unique and complex structure in price as you move across the city. So if we wanted to model that structure in price across the city, like where are there more expensive houses and where there are less expensive houses in this city, we have a lot of options that we could try to use to try to model that. One option we have is to use splines. So we can use splines to build new features for modeling. The thing is, though, we would have to decide how many spline terms to use. So this line right here shows 2 spline terms, and that doesn't look like it captures the real structure very well. 5 looks better. I would believe 10. 10 looks pretty good. 20 seems okay. Okay, can you hear me again? I just got a notification that I was muted.
Yes.
Okay.
Yes. Now
Okay.
yes.
Okay. Weird. Okay. It just muted me. Okay. Maybe I hit a something on my keyboard. Sorry about that. Okay. All right, so 20 seems okay here, but I'm starting to feel a little bit skeptical. And at 50, I no longer believe this. Like this, I don't believe this at all. And at 100, this is just silly. Like adding 100 spline terms is just a silly thing to do. So what's great about data visualization during the process of EDA is that we as machine learning practitioners can see and absorb this and then use it to make decisions that are then captured in code. If you are a Tidy Models user, your code might look like this, with a feature engineering recipe defined with steps that transform and prepare our data to get it ready for modeling, whether that's dealing with the factor levels, creating indicator or dummy variables, or setting those 10 spline terms, as that last line does there in this recipe. So whether it's for engineering new features or choosing an appropriate model or understanding data quality, data visualization during EDA has a huge impact on what model practitioners do later on. So in some ways, it's the foundation on which the rest of the model is built. So it is often possible to estimate the best answer or value or option for some of these choices that we've been talking about using empirical methods. For example, you could tune the number of spline terms using resampled data sets, but it is nearly impossible to remove entirely the element of human judgment from these choices, or at least it's a bad idea. So machine learning algorithms are astounding. They're incredibly capable of learning patterns from large amounts of data. So vigorous adoption of EDA as a part of the machine learning process is one safeguard that we have against ending up in a situation where you have to ask yourself whether it was a good idea to just deep fry your data. So let's now move on to that second phase. So we've talked about EDA and how it impacts modeling. And then now let's move on to talk about model evaluation. This is a phase where we have trained and possibly tuned models. So we have predictions to compare to true values, and we can assess how our models are performing. And again, let's ask this question: why are these plots built? At a very high level, these plots are built to understand the models. And here we're working on assessing model performance. This is the point at which we as model practitioners have to reckon with questions about success and failure. Did this model work? Machine learning practitioners often need or want to try out several different kinds of models. And so model evaluation is where we compare models and ask which model performed best. The process of model evaluation also allows us to interrogate subgroups. And this is typically where discussions of model fairness come in. A lot of current work on machine learning bias and fairness focuses on how models perform differently for different groups. Maybe for different classes that may not have been included directly in the model as a predictor. But if you look at the output of the model, we see differences in performance because maybe our predictors included something that was a proxy for these things that we care about at the end. Model evaluation is also concerned with understanding why a model is making the predictions it does. And for all of these questions, practitioners heavily use data visualization for a lot of the same reasons that it's used during EDA, which are largely the same reasons that anyone ever uses data visualization. These plots are used to ask and answer these questions to show relationships clearly that would be difficult to see otherwise. And they are supports and aids for making the decisions that need to be made. At this point, the decisions are things like, which model do I choose? Is this model fair? And again, we're at a point of important human decision, and these visualizations are an aid or support for the human decision. There are some pretty unique things about plots used for model evaluation that I think are cool to highlight. One is that a lot of these plots used for model evaluation involve graphical norms or idioms. So this plot shows how two metrics, RMSE and R squared, change with the regularization parameter, like the penalty for a lasso regularized model, like how regularized it is. So someone who is familiar with these kinds of models can look at this plot and quickly recognize whether or not it worked. Whether it's a model that need a lot of regularization or a little bit. And looking at that R squared, assess how well, or not in this case, the model fit the data. So it's like a shorthand or an idiom that packs a lot of information in it for a familiar audience. So this plot is similar. This is a receiver operator characteristic curve. Well, it's 10 of them actually here for a model that's trained on that Palmer penguin data that we discussed at the beginning. And it's a visual representation of how well a binary classification model is doing. So the more up in the left-hand corner the curves are, the better the model is doing. So the axes have the true positive rate and the false positive rate on them. And ideally, we want both of those to be great. We want the model to be able to do a great job at identifying both of those cases. So this is another example of a model evaluation visual idiom that is very familiar to modeling practitioners. That is like a familiar language used by modeling practitioners to communicate quickly and pack a lot of information. It can be used to compare models, to assess a model, and so forth. And for these kinds of visual idioms are a great fit for automatic plotting methods. So when we talked about EDA, I highlighted the need for a really flexible plotting framework that can be used to create any kind of plot fluently. And we should adopt a grammar that lets us, like a visual grammar that lets us create any kind of plot we want in a really flexible way, in the same way that a language grammar lets us put together any sentence that we want. So a lot of model evaluation plots are the same every single time we make them. And practitioners can be better served using shortcuts. These automatic plotting methods built by tool builders like my teammates and me, because it can be a hassle to copy and paste the same code for an ROC curve every single time. However, at the same time, not all plots for model evaluation are these kinds of standard norms or idioms that are considered very common, in the modeling communities. So this is an example of an evaluation plot for a model predicting the class of a volcano. And each hexagon shows the percent of the volcanoes that have been classified correctly within that area on the Earth. So while knowing about some key automatic plotting methods are a useful part of the visualization toolkit for a machine learning practitioner, still, having that fluency and a flexible visualization system is extremely important. There's not always going to be an automatic method or one of these idioms to visualize model performance in the way that you need to. So far in our discussion of model evaluation, we've focused on plots like these that focus on some kind of metric, like accuracy or RMSE or something, like some metric along those lines. Model evaluation activities can also encompass model explanation. And discussions of fairness, for example, often will either look at metrics by subgroups, or we'll look at model explanations. And visualization is also a key tool for explaining models. There are two kinds of model explanations. The first one are global explanations, where we evaluate what features are important in a model predictions overall. So this plot is from that data set of trees in San Francisco, again, and the length of the bars here corresponds to how important that feature is in predicting whether or not the tree is maintained by the Department of Public Works using a random forest model. So having a private caretaker is the most important predictor. The latitude and longitude are the next two most important. So that spatial information is really important in predicting who maintains the tree. So these are examples of global feature importance. Why is the model making the prediction it is? These are the things driving the predictions overall for the model as a whole. The other kind of model explanation is a feature explanation at the individual observation level. So this is also called local feature importance. So there's multiple ways to do this. This particular plot shows an example of a Shapley additive explanation. It's for a single passenger on the Titanic, for one passenger on the Titanic, and a model predicting whether or not he would survive. And the Shapley value there is the average contribution of a feature to the prediction in different combinations, or what are called coalitions. Like if we have different coalitions of features, how much do they contribute? So the bars show the average, and the box plots show the distributions of the value and all the different coalitions that were tried. So for both global and so overall, and then observation level, which means for one observation, for one data point, for like one person in this example, these plots are used by the creators of the machine learning systems to evaluate and understand the system. So at this stage of the modeling process, we're again at a point of important human decision, and model explanation together with model performance can be used to make choices about which models to use. So through this whole exploration of data visualization in the machine learning process, we focused on plots made by system designers and operators for themselves as a tool to make better modeling choices. So these are plots made by practitioners for practitioners. Often when we talk about data visualization, we center its function as a communication tool to people outside, and it absolutely 100% is a communication tool. But we can also think about some of data visualization's other functions, like its ability to be used by system designers to understand the system more fully. Recently in the machine learning community, I've been interested to follow some discussions around what have been called participatory approaches to machine learning, where the people designing the system purposefully partner with the people impacted by the system, like the users of the system, in shaping and designing it. I think this is going to be really interesting to watch, because that kind of practice or approach is going to have to impact choices through the whole modeling process, that whole schematic that I showed you, including what kind of plots to make. Like, it's going to impact who is the audience for those plots, and we'll have to impact, like, what do we assume about what people know in order to interpret those plots and whatnot. It may change the answer to this question, who are the plots for? What I don't think it will change is the main purpose of any given data visualization. Some plots are created to help us understand the data that we start with. This is the input for the models that we create. So investing in data visualization to understand the data is like laying a strong foundation. Some plots are created to help us understand the models that we create, and this is the output. So careful visualization practices in model evaluation sets us up for success in models that are as accurate, as appropriate, and as reliable as possible. And with that, I will say thank you so much. I want to be sure to thank my teammates on the Tidy Models team, as well as the folks who organized the Tidy Tuesday project. So Tidy Tuesday, if you haven't heard about it, is like a weekly social data project that anyone can participate in, and most of the data sets that I shared today are from that project. So I think I have time for a few questions. I can look through the chat a little bit and find some questions.
Thank you, Julia, for this great talk. That was really incredible. Personally, I learned a lot from you today. So thank you all for your attention. And as you said, let's just move to the questions. So there was Zach who's asking if you could please explain more about the tuning.
Ah, great. Yes. So models have parameters that we can estimate when we fit them. You know, so with the example of like linear regression using ordinary least squares, we can estimate the slope, and then the parameters go for each coefficient as we fit them. But some models have parameters that cannot be estimated from the data when we are fitting them, and sometimes we call these hyperparameters. So some examples of these are, if you're fitting an XGBoost model, like how many trees, or like how many, and then how many, like what proportion of the data are you going to expose at each node? Or in the splines model that I showed with the houses, how many splines are we going to use? So instead of, we can't estimate that parameter when fitting the data. So instead, what we can do is we decide on a bunch of possible values, and we fit all of them, and then we evaluate the model and we see which ones perform best. So this is the process, this is roughly the process of tuning, where we say we are going to find the best value. We're going to estimate the best value for some hyperparameter by trying a bunch of different ones and see which one works out best. So this is what we do for values that we cannot estimate from training data, from one data set. So I will find a link here and drop it into the chat that maybe walks through how to do that.
So thank you, Julia, for making this clear for Zach. I hope that helps him. And so we have another question from Michael. He was asking about what's a graphical norm or audio. So he was asking about that when you showed the volcanograph. What kind of plot would you recommend for understanding variables, or how much a variable contributes to prediction?
Yes, okay. So I think that question I think came out the first time I said what is like a graphical norm idiom, and then I walked through quite a number of examples. So I think by talking about examples of what they are, I think we went over, what we mean by that. And then let me see if I find that next. I think, can you say that last part again? Okay. So what kind of plot is best for understanding variables?
Yes.
Yes. Okay. So, so often the kinds of, like when we want to, so I went and okay, so this was asked when I showed the volcanograph, and then we went on to kind of look at exactly that, plots for understanding how much variables contribute to prediction. So that is model explanation. So we looked at both global and local feature importance, and people, the kind of plots that people use for those are often, box plots, bar plots, if you're looking at a distribution or an average or a single value. So those kind of plot data visualizations that people use for model explanation, depending on if you're, like what are the specifics of the kind of numerical values that you have. We use the same kind of rules there, but we walk through a couple of examples there.
Okay, great. Hope that helps you. So we have another question from, in fact, this is not a question, but Fernanda is asking about how to get involved in Tidy Tuesday.
Yeah, Tidy Tuesday is open to everyone. So every, I believe, Monday, the new data set is posted, and then like Tuesday, or I don't always get to something on Tuesday, but Tuesday and then later in the week, people post a plot or something that they are interested in sharing with folks. So it is something that's totally open to everyone. So I can try to find the link, and
I'm just sharing the link in the chat. It's okay.
Yes, great.
We already shared the link with the participants.
Yes.
Fantastic. Yeah, Tidy Tuesday is something that's wonderful to, as you know, what I really like about Tidy Tuesday is that it's like just like not a huge deal, and it's kind of like just like a little thing every week, and it's like, oh, okay. And if you don't do it some week, it's great, and if you have time some week, great. Like no big commitment, but a way to kind of do things with other people in community. That's what I like about Tidy Tuesday.
Okay, that's great. So we have here Ines. Thank you, Julia. Great presentation. What's your favorite visualization representing a model and aiming for stakeholders buy-in?
Yeah, so a lot of what we talked about today was visualization used by, here, I'm going to stop sharing here. A lot of what we talked about today was visualization used by system designers during the process of building, like visualizations by practitioners for practitioners, and less about the communication externally. And I think there's a lot to think carefully about when it's time to communicate externally with stakeholders about the model. And some things to consider, I think, are like, how much do you need to explain about the model to your stakeholder? Have they seen a plot like that before? People tend to respond well to things like, bar charts. They've seen it before. People understand, people love maps, but something like, say, that, like an ROC curve, if like someone has not seen it before, they're like, why are you showing me this? Like, is it good or bad? So I think that that it varies a lot from organization to organization, and there needs to be careful thought put into how am I going to best communicate to my specific stakeholders what they need to know. So those are really decisions that a lot needs to go into.
Great. Great, Ines, for you. So we have here Binur. So I want to know what you think about MR3 process-wise and performance-wise, and what are the future updates we can wait for the Tidy Models package?
Yeah. So so in R, there have been multiple sort of takes on this question of like, we want a unified system for modeling. So you know, if you're someone who does modeling in Python, you may be familiar that like there's scikit-learn, right? And there's like just scikit-learn. And in R, you know, we have dozens and dozens of interfaces to models, and then we've had a few different attempts of like, oh, I don't want to learn dozens, 20, 30 ways to interact with model. I want to learn one. And so Carrot was one attempt at that. Carrot was built by Max Kuhn, who's now building tidy models, and I work with Max. And MLR3 is another system like this that has built to like to have a unified interface. And there's a lot to like about MLR3, and I think that and if it's something that you use and you like, I think that you should keep using it, and you should you know, not feel bad, or you should enthusiastically use it if it works for you and you like it. I think that some things that Tidy Models offers that would be reasons to think about using Tidy Models is like the fluent integration with the tidyverse. And so if you're someone who likes the tidyverse, you may enjoy using tidy models for your modeling and machine learning needs. But MLR3 is great and well designed. Some of the things we're working on right now in the tidy models ecosystem are better support for parallel processing, especially on all operating systems. Like achieving parity on, say, like Windows compared to Linux and Mac. We are also working on survival models in the near term. And one thing that I'm always interested in is further expanding support for being able to do a really great job with text modeling, so like natural language processing and text modeling within tidy models. So one thing we recently did, and that is better support for sparse data in like sparse matrices within tidy models. So those are a couple of answers there. Oh, I see it. I see the next thing that is very related. Someone asks about like, should they use Carrot first? Should they learn Carrot first or tidy models? And if you're already a Carrot user, Carrot is going to continue to be maintained, but no new features are being built for Carrot. For those of you who don't know, Carrot and tidy models have the same maintainer, Max, who I work with. So Carrot is not going away. It will continue to be maintained, but no new features are being built for Carrot. So if you have existing projects in Carrot, no reason to freak out. But if you're going to start something new, I recommend starting it in tidy models. So, and if you're starting to learn, I recommend starting with tidy models. Like if you've not started something, don't start something new in Carrot, because new features, better support, like that's all going to be moving to tidy models. So I think that that's the situation with Carrot and tidy models. Continuing to support Carrot, but no new development, no new feature development.
Okay, thank you. So you have here just two more questions more from Mahmoud. Most of time, the result of blending is worse than my tuned light GBM model. Is it because I use the same features, or because my ensemble models are mostly base tree models?
Okay, so like I think this is a question about ensemble modeling, like stacked modeling, I think. And the stacked modeling sometimes is worse than just like a gradient boosted model. So this is a hard question to answer, depending, because it really depends on characteristics of data. And like for some specific data sets, stacking does work really well, and in some others, it does not. I think that Yeah, so if your ensemble models are mostly tree-based models, then you're kind of doing gradient boosted trees. You're like ensembling trees together. You might, if you're interested in ensembling models, you might take a look at the new Stacks package. I think it's not quite to Cran yet, or it might have just gone to Cran, I forget. But so it's at, you can look at it, find it at stacks.tidymodels.org, and it is a package for stacking, for ensembling many different kinds of models, and it is really nice how it is turning out. So it might give you some insight if like when and where your ensembling models are not your stacked ensembling models are not working as well as you think. Like this idea of a super learner, you know, if you've heard about that, like, hey, let's put all the models together, that kind of situation. But that's a little hard to answer without knowing a lot of specifics about the data. All right.
Okay, so just last question.
Okay.
Do you think software like Tableau, Power BI, or ClickSense have some limitations comparing to data feeds with R or Python?
Yeah, so I think that things like, so I've been in organizations that use things like Looker or Tableau, and they can have real strengths when it comes to being able to share broadly across the organization things that you want to get out broadly, you know, like to, you know, everyone, you know, across business stakeholders, like, here, look at this visualization that we decided is an important one for everyone to see. When it comes to quick iteration, that's where I feel like the big limitation is that the ability to when I mentioned that, like, oh, one of the big things that gets you a huge step forward in quick iteration to being able to make the right choices for building models, we need this fluent system for flexible data visualization. That's what data visualization in something like something that has a grammar of graphics, like in R or Python or whatever, gets you. And so that, I think, is the biggest. They're you know, they're a little bit like apples and oranges, that they're not there for the same purpose. So yeah, there's definitely I would not use something like Looker or Tableau to do exploratory data analysis to get ready to build models. But, you know, I would use something like Looker or Tableau to build a dashboard for, you know, everyone in my organization to be able to come and look at later. So I think they can have different purposes. It was really, yeah. So I was just saying, it's been really great to speak with you all, and these were really fantastic questions.
Thank you. So I think you are done with the questions. Thank you all for your attention. Thank you, Julia, for this great job and for accepting to be between us today. So just keep in touch, dear participants, and stay tuned to our upcoming events. So, Haifa, I don't know if you want to add something.
Yes, I want to thank Julia again for accepting our invitation, and it was a really good presentation. We learned a lot about data visualization for machine learning models. Thank you again, Julia.
Thank you so much for having me.
Thank you all. Goodbye.
Thank you so much for all attendees. Thank you. Goodbye.
Goodbye. Thank you. Bye, Mike.